Good morning and welcome back to the next section. This is an exciting section because I get to introduce you to a whole new number that you have never used before. And this is exciting. I like this number. This is the number E. Yeah, I missed a few days of Sesame Street, but yes, the number E. The number E is an irrational number, kind of like pi. This is my second favorite irrational number too, so that's why this is so exciting. A lot of people think, pi must be my favorite. Like, no, pi is a distant third at best. E is way cooler than pi. And you might be wondering what my favorite is. That's phi. That's the golden ratio. We're not talking about that today. Anyway, the natural base, E, and E is also called the natural number. So before we get too far into that, let's look at what our learning targets are for the day. Our learning targets, I can use the number E to write and graph exponential functions representing real-world situations. And yes, we will say the number E many, many times. And I can solve equations and problems involving E or natural logarithms. Exponential growth and decay with half-life, radioactive decay, that's going to involve this kind of thing. So, let's look to see what is E exactly. The natural number. E is, again, it's irrational. It's about 2.718281828459045. You don't need to remember all that. There's a button for it on your calculator. It's usually right around the log buttons. On the graphing calculators, it's a second and then it's a ln. It's right above that. It's e to the x. It's on the left-hand side. Anyway, there's a great story of how I remember that many digits of it, and I don't know what the next one is. We use E with increase and decrease type things, exponential growth and decay. We're going to start out with the basic percent increase equation. This is one we saw at the very beginning of the chapter. A equals P times 1 plus R to the T, where A is the final amount, P is the principal or initial amount, R is our rate as a decimal, and T is the time. And we had plus or minus. Right now we're just looking at increase. Decrease we'll put the minus somewhere else. Anyway, we use this a bit, and we're actually going to use it again today. But with this, we can get a slightly more complex equation. And we add these n's in here. So this talks about compounding. How often does it happen? Up with the basic one, we had to make sure that the rate and the time period, they agreed with each other. Usually it would be the percent per year and then the number of years. Well, sometimes it's different than that. Sometimes the rate might be percent per year, but then it happens quarterly, which would be 4 times in a year. Well, if your rate is 4%, they don't give you 4% every quarter. They give you 4% divided by the number of times it happens in the year every quarter. So they'd give you 1% each quarter, but then it happens 4 times as often. It could be compounded monthly. Some bank accounts are compounded monthly. At the beginning or end of each month, they will take whatever you have and add a percentage onto that. It could be compounded weekly or daily or every hour. And what we're going to see is what happens when that n gets really, really big. But before we make that n get really, really big, we're going to make some of these other variables go away. And not go away. We're just going to say that they're just going to be 1. Just for the sake of argument. We're going to start with 1. Our rate is going to be 1. That'd be 100%. And time is 1. And now, what happens when n gets really, really big? We could graph it at this point. And when we do, we see that there's an asymptote. And that asymptote is y equals e. It's 2.7, so there's 2.5. It's almost halfway between 2.5 and 3. And so as n gets really, 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 really big, this whole mess becomes e. It becomes this number up here. And so that allows us, with some algebraic manipulation, which we don't need to worry about, it allows us to get a percent increase for it being compounded continuously. Every fraction of a second, this thing is compounded. And that equation is PE to the RT. It's PERT. And I use it to wash my hair. Anyway, the A is still the amount. P is still the principal. E is this number up here. R is your rate as a decimal. And T is the time that it takes. And again, the rate and the time should agree with each other. If something's happening hourly, the time should be number of hours. If it's yearly, it should be number of years, etc., etc. And so it uses the exact same variables as the percent, the basic one. So let's look at a problem. And this is going to be a video problem. And so we're going to watch this short clip. Lasts about 49 seconds, give or take. And then we're going to get pieces. We're going to figure out what these numbers are, and we're going to solve the equation, figure out how much money is left. So let's listen.
Do we have enough money to pay Bender's fine?
78, 79, 79.50. Crud! We're 50 cents short. Hey, that's my old bank. Maybe my account's still open.
We don't seem to have your retina scan, your fingerprint, or your colonic map on file.
Yeah, well, I did open the account over 1,000 years ago. What about my ATM card?
Do you still remember your PIN number?
Sure. It's the price of a cheese pizza and a large soda back where I used to work. Panucci's Pizza.
Okay, you had a balance of 93 cents.
All right.
And at an average of 2.25% interest over a period of 1,000 years, that comes to 4.
Alright, so let's see what we need to find. First of all, we're going to need to find the P, the principal, how much do you start with, the rate, what was our rate, and how long was it invested for. So let's watch that last little bit again so we can pay attention for these three pieces.
Okay, you had a balance of 93 cents.
All right.
And at an average of 2.25% interest over a period of 1,000 years, that comes to...
Alright, so what do we have? We had a balance of 93 cents, a healthy checking account, a rate of 2.25%, which would be 2.25%, or as a decimal, 0.0225, and the time, 1,000 years. You know, when you're frozen for 1,000 years, time flies. And we can plug these into our equation. So if we start out with our basic equation, A equals P times 1 plus R to the T, we can plug in P, we can plug in R, and we can plug in T. And at this point, it becomes a calculator problem. We're going to add these two guys together to get 1.0225 to the 1,000th power, enter, and then times 0.93 to get A equals, this would be $4,283,508,450. Seems like a lot. Remember, exponential functions grow really fast, and it's been sitting there for 1,000 years. So that was with the basic increase. Let's see what it would be if we were compounding it continuously. We're going to use the same numbers. We'll have 0.93 times e to the 0.0225 times 1,000. Let's multiply these guys together first to get e to the 22.5. We're going to go e to the power, again, there's an E button. There's actually two of them in your calculator. We're going to go e to the power first, and then times 0.93. Don't multiply 0.93 and e first. That would be bad math. So e to the power times 0.93, and we end up with 496,785. No, $496,785,519. So that was a significant difference. It's looking $1.2 billion more, which if you don't think that's significant, if you can just let me have that, I'll take that off your hands, no questions asked. So, being that it came here, this one wouldn't be realistic for the problem. We don't usually deal with money with compounded continuously stuff. This one is. So let's see if this nice little cartoon show did its math.
Interest over a period of 1,000 years, that comes to $4.3 billion.
And so, at this point, this clip didn't quite get into it. He started foaming at the mouth and passing out, which, if you were just told that your 93 cents was now worth $4.3 billion, you would probably do the same. 4.3, that's a nice round. I mean, that's just a little rounding thing. I love it. The show, Futurama, actually does its math. Mathematicians on staff. It's fantastic. All right, so, but we saw how we did older problems, and we saw how we use this new equation. They're both calculator things. None of them, it doesn't take any real thought. You just set it up, plug it into your calculator, and you get your answer. It's probably not going to be a pretty number, but that's okay. So, that's the natural number. That's E. Well, with the natural number, and since we have it as a base of exponents, we're going to have a logarithm that goes along with it. And the log that goes along with it is called the natural log. The natural log, the symbol, instead of a whole log, L-O-G, it's ln. That would be log natural. But ln of x is defined to be the log base e of x. Just like if we had log x, that would be the log base 10 of x. The two logs that your calculator will do, and has been able to do for quite a while, are the standard log, log base 10, and the natural log, log base e. In fact, some calculators, the TI-89 for example, the natural log is really easy to access, and the log base 10 actually takes a bit more effort to get to. On the calculators that we have, it's about the same. They're actually right next to each other. The buttons are. And so, the natural log, just like E is a number, the natural log is just a log. All the stuff that we did with logs still holds true with natural logs. There's no difference. We have some properties. Our inverses. Natural log of e to the x, well, the base and the base are the same. It's just x. The other inverse, e to the natural log x, base and base are the same. It's just x. The addition properties, if we add things, means we multiply on the inside. Same thing if we subtracted them, it would be a divided by b on the inside. The power property, all of those still hold true. And so we'll be doing some simplifying with logs, with natural logs. So we could have things like the natural log of e to the x minus y. Well, natural log of e to the something, natural log of e to the something is just a something. In this case, it's going to be just a something. If we want to show work, we could take this using the power property, moving it out front. So we have x minus y, natural log e. The base and the base are the same. E to what power equals e. That's just 1 equals x minus y. But we could just go from here, hey, that exponent, it just equals the exponent because of this property. Same thing with this one. E to the something, or e to the natural log of something, it's just a something. It's just a 2x. We can make it a little bit harder. E to the 3 times natural log of something. Now, people always want to say, oh, it's 3x. No. We need e to the natural log of something. So how could we deal with this 3 being multiplied in front of a natural log, in front of any log? We can use a power property in reverse. We can take this 3 and move it up to be an exponent. Now we have e to the natural log of something, and so it's just a something, x cubed. So that's simplifying. These are basically the same as the ones we were doing in the first half of the chapter. It's more log practice. We can solve as well. If we have something like natural log 10 plus natural log x squared equals 10, there's a couple ways we could do this. Natural log 10 is just a number. We could find it and subtract. It's not going to be as pleasant, though. I like to not come across the ugliness quite so quick. So let's do some other stuff first. Let's combine these two. We can combine these two using this property. We just multiply them together on the inside. So we have natural log of 10x squared equals 10. Now we can write it as an exponent. This is e, so e to the 10th equals 10x squared. Well, e to the 10th is just a number. You can find it. I had mentioned that the e button is on the left side of your calculator. It's second natural log. And so we can do e to the 10th is 22,026 point something something something. Nobody cares about that right now. Leave that number in your calculator. Divide it by 10. So we get x squared equals 2202 something something something. Again, leave it in your calculator. Square root. And so we get x equals plus or minus. And now we can have a few decimal points. 46.93. Now notice from this whole time, like I did not use 22,026. I used 22,026 point blah 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 blah, whatever was in my calculator. Do not delete it and type it in again. Same thing we've been doing. We'll be doing it again in the next problem. But the solving, we get it to be just one log using our properties, and we can get rid of it by writing it as an exponent. It's just a number, and then we can solve for x. So, an application that we'll see quite a bit, because things that are compounded continuously are things that don't care about years, months, days, hours. Those are all human constructs. Yeah, we like them, but things like radiation doesn't care that, ooh, it's been an hour. I need to do something now. It just continuously happens. And so, with this, we're going to use our continuous growth / decay equation. However, this one works with money, just because P is the principal, R is the rate, T is the time, A is the amount. That's great. We're going to change it up just a little bit. We're not changing the equation. We're changing the variables. We can write it more like this, where N, instead of being the amount, is the number. I know the amount and number are the same. And naught is just the initial amount. It's the same as the principal. The 0 isn't times 0. It's just saying that at time equals 0, how much was there? So it's the initial or the principal. The E is the same, the T is the same, and the R just changes to a negative K. That's the decay constant. If you forget that there's a negative there, the first thing we do is we find K. K will end up being negative, and so it will put the negative in there for you. Most of the time when you have a problem like this, it'll actually give you this equation, such as this problem right here. So this is a physics problem, and it says technetium-99m, a radioisotope used to image the skeleton and the heart muscle, has a half-life of about 6 hours. Find the decay constant, then use the decay function, this one that we just looked at, to determine the amount of a 250 milligram dose that remains after 24 hours. So the first thing we need to do is we need to figure out what in here is actually important in doing the problem. The thing that gets people is this 99. Has nothing to do with the problem. That's just part of the name of this technetium. It's the specific isotope of that element or compound, something. And so this whole first line doesn't have anything to do with the problem. It teaches you something. It sets it up. It says, hey, this is useful here, but as far as solving, we don't need to worry about that. So the first thing is finding the decay constant. Of this information, the only thing we need to know to find the decay constant is the half-life. And what a half-life is it says that this amount of time, half of it will be gone. So after 6 hours, we're going to lose half of it. After another 6 hours, we'll lose half of what's left. And then after another 6 hours, we'll lose half of that. So that's what a half-life is. We're going to use our equation and plug in what we know. We know that T is going to be 6 for 6 hours. And what gets people is, well, how do I know how much I start with? Who cares? I would start with 1. You could start with a number that they give you, but just start with 1. Because after 6 hours, how much will be left? 1/2. If you start with something else, like let's say you start with 100, after 6 hours, 50 will be left. Let's say you start with 8, after 6 hours, 4 will be left. The very first step is to divide by this number. When you do, you're always going to get 1/2 equals e to the something. The 6, instead of having negative k times 6, just made it negative 6k. So we have 1/2 equals e to the negative 6k. Now we need some way to get our variable here out of the exponent so that we can deal with it. And you might be thinking, wait a second, I remember this from yesterday. If you're thinking that, great, because that is ideal. To get the variable out of the exponent, we take a log of both sides. Being that we're dealing with e, I would take the natural log of both sides. You could take the regular log, the standard log, but it's going to be extra steps. They're both logs. They're interchangeable. Sometimes natural log is easier. Sometimes standard log is easier. I resort to natural log. That's my go-to. It's more useful in more situations. But yeah, you could do either. For these, I recommend natural log because we have this. Our exponent can come out in front to give us that. Natural log e is just 1. So that goes away. We have natural log 1/2 equals negative 6k. Natural log 1/2 is just a number. It's about negative 0.69. Divide by negative 6, and we get k is about 0.1155. That is the decay constant that we were finding. Find the decay constant. And this will be true for this whole problem. Everything about this technetium-99m, this is the decay constant. Am I going to use this in the problem? No. I'm going to use the whole number that's in my calculator, because it is going to be an unpleasant number. So now we can use the decay function to determine the amount of a 250 milligram dose that remains after 24 hours. So we can start out with our equation and plug in what we know. We know the time is going to be 24 hours. We know the k is going to be this number that's in our calculator. E is E. And our starting amount is 250. So we can plug that stuff in. And this is function notation. It's n of 24, the amount after 24 hours. So to do this, this number's in my calculator. I'm going to multiply by negative 24 to get about negative 2.77. I'm going to go e to the answer equals, and then times 250 to get that after 24 hours, we're going to end up with 15.625 milligrams of technetium-99 still in the system. And so that is how you do it. There's a couple different variations here. Here we were figuring out what N of t is. It's possible they'll give you the amount. You have to figure out the initial amount. After 24 hours, there was 250 milligrams left. How much was there in the beginning? And so this is your variable. Well, you'd still find this the same. It's just a number. Divide by it. So you get your variable equals a number. The other thing it could give us is t. Finding t, you take this and divide. And then natural log of both sides is just like finding k over here. So it's all the same. In this case, we didn't even have to use the equation to do that. We could have just made a table. Because we know at time 0, there's 250. 6 hours later, we're going to have half, 125. 6 hours later, we're going to have half of that. Other 6 hours, we're going to have half of that. And another 6 hours, it's going to be half again. And we get that same amount. So you might be thinking, well, why do we even do it this way? Well, what if it said 25 hours or 20 hours? This way worked because the 24 hours is a multiple of 6. It goes in evenly. If it's not, you have to use the equation. We use this one so that we could see it both ways. Anyway, today there's great stuff, natural logs, and a whole new number, e. It's very exciting. Growth and decay problems. Oh, lots of fun stuff. Anyway, I hope you enjoyed. Don't forget to post a comment, and I will see you in class.